Many real problems involve time dependence, and obviously the plane strain compression model that I started this session with involved time dependence. To incorporate this, we need a discretized expression for the time derivative, and I show that here as partial dt by dt is approximately equal to 1 over delta t, the time interval, multiplying the temperature of the node Mn at time interval p plus 1 minus the temperature of the same node at time interval p, where the time between these two time intervals is simply delta t. Substituting this into the generalized two-dimensional heat transfer equation gives us the expressions shown here. So this is the partial time derivative that I've just written down. On the right hand side we have the heat generation term, and then we have the expressions for partial d2t by partial dx squared and partial d2t by partial dy squared, expressed in terms of nodal temperatures as I've outlined already. The only difference is this time these are the nodal temperatures at the time p. And this means there's only one temperature that appears in this equation at time p plus 1. All of the other temperatures are at time p, and this is known as a forward difference or explicit approach. If we now take that equation and consider the case for a square grid, so that delta x equals delta y, we can simplify the equation slightly as I've done here, and you'll notice that I now have an expression on the right hand side for the temperature Tmn at time p, which involves 1 minus 4 alpha delta t over delta x squared. I want to consider this in the case of there being no heat generation, so I've simply taken out this term and set q dot equal to 0. So otherwise this expression is the same. I now want to consider a specific case of the node Tmn is at a higher temperature than the 4 surrounding nodes, and those 4 surrounding nodes are all at the same temperature at some time p. If I then consider the case of delta x squared of alpha delta t is less than 4, and just to make this more obvious I'll take a very specific case, namely that the value of delta x squared over alpha delta t is 2, but this would work with any other number that was less than 4. Then I've already said we're dealing with a case of no heat generation. Using that information and this equation that was on the previous slide, I get that the node Tmn at time p plus 1 equals a half times 4 times the nodal temperature n plus 1n at time p. Remember, these nodes all have the same temperature, so I can simply write down the temperature of the sum of them as being 4 times the temperature of any one of them, plus the temperature of node Mn at time p times 1 minus 4 over 2. Putting that together, I get that the temperature of node Tmn at time p plus 1 equals 2 times the temperature of one of the adjacent nodes at time p minus the temperature of the node Mn at time p. But remember, I started out by saying that we would consider the case that the nodal temperature Tmn at time p was greater than the nodal temperature of Tm plus 1n at time p. So the second term here is more than half of the first term, and that means that this difference must be less than the temperature of the node m plus 1n p. So in other words, the temperature of node Mn at time p plus 1 is less than the temperature of the node m plus 1n at time p. Now that might sound a bit abstruse and abstract, so to make things clearer, what I've done is I've taken some specific numbers here. The numbers as such are arbitrary, apart from the fact that what I'm saying is the temperature of the node Mn at time p is greater than the temperature of the 4 surrounding nodes at the same time p. For simplicity, I've set the temperature of the 4 surrounding nodes to be 1 and the temperature of the node Mn to be 2. That means the temperature of Mn at time p plus 1, when we substitute it in the equation on the previous slide, equals 2 times 1 minus 2 equals 0. So if we looked at the temperatures, what we would have is this is our initial situation, a higher temperature in the middle surrounded by 4 lower temperatures. These equations would then give us a result where we ended up with a lower temperature in the middle surrounded by a higher temperature. This is clearly physically impossible. And the reality is that the minimum possible value of that central node has to be the same as the temperature of the surrounding node. So in other words, if I go back to this slide, the minimum possible condition is these nodes are all at 1, and so is this node. This is not what comes out of these equations if delta x squared over alpha delta t is less than 4. This means that once you've fixed the size of your mesh, you've fixed the maximum time interval that can be used. In 2D, it turns out that this maximum temperature interval is given by the equation delta x squared over alpha delta t is greater than or equal to 4. If you were working in 1D, very similar equation, except it would be greater than or equal to 2. Things become a bit more difficult at boundaries because the maximum time increment is then also influenced by convective heat transfer, and I've shown the equivalent expressions here for boundary elements where we now involve the mesh bio number. It is possible to avoid this problem by using what's known as a backward difference or implicit formation, and in this case the nodal temperature Mn at time p is actually related to the temperature of the surrounding nodes at a future time p plus 1, plus the temperature of the node Mn also at the future time p plus 1. In this case you can't actually obtain the temperatures at p plus 1 directly in terms of the temperatures p, and you actually have to write down the equations for all the nodes and solve simultaneously each time step. Although this is strictly more involved, it may be faster because in this case there is no limit on the maximum time step that can be used. That said, the plane strain compression model that I showed you at the start did actually use a forward difference approach, and there were specific subroutines designed to calculate the maximum time interval once the mesh had been deformed. So overall, what I've done in this session is briefly go through finite difference methods for dealing with calculations involving convective heat transfer. I initially went through some problem from last time involving Gauss-Seidel iteration, and then I incorporated convective boundary conditions, and then in the latter part I briefly looked at how time dependence is included and the difference between what's known as a forward difference or explicit approach and a backward difference or implicit approach. Thank you.